Mercury sits closer to the sun than any other planet. Daytime temperatures hit 800 degrees Fahrenheit, hot enough to melt lead. So here's the question nobody thinks to ask. What's happening inside a planet that gets cooked like that every single day? Scientists just found the answer, and it's the opposite of what basic physics says should happen. Mercury isn't just hot on the outside. Something inside it is refusing to fully solidify. And the reason why is something researchers didn't expect to find anywhere in the solar system. Stick around, because by the end of this video, you'll understand why Mercury might be the strangest planet in our solar system. Not Mars, not Venus, Mercury. When you think about space exploration, what comes to mind? Mars rovers, Saturn's rings, maybe Jupiter's storm. Mercury almost never makes the list. And that's strange, because Mercury is the closest planet to Earth on average, closer than Venus even. You'd think we'd have sent dozens of missions there by now. We've sent two missions, ever, to the planet nearest our own. Compare that to Mars, which has had more than 50 missions attempted. Mercury has been visited by Mariner 10 in the 1970s, which only flew past a few times, and Messenger, which didn't even arrive until 2011, and only after taking a 7-year looping path through the solar system just to slow down enough to get captured by Mercury's gravity. Why is the closest planet the hardest one to reach? That question actually matters for what we're about to get into, because it explains why Mercury has stayed a mystery for so long, and why what scientists just found took nearly 50 years to uncover. Here's the part that surprises most people. Getting to Mercury isn't a distance problem, it's a speed problem. The sun's gravity is so overwhelming that close to it, everything moves incredibly fast. A spacecraft trying to reach Mercury doesn't just need enough fuel to travel there. It needs enough fuel to slow down once it arrives, or it just gets flung right past the planet by the sun's pull. Slowing down that much takes almost as much energy as launching in the first place. That's why Messenger's route to Mercury involved flying past Earth once, Venus twice, and Mercury itself 3 separate times, using each flyby like a brake pedal, before it could finally settle into orbit. So for decades, Mercury has essentially been the solar system's locked room. We knew it was there. We knew a few basic facts. But what was actually happening inside it stayed a mystery, until a discovery back in 2007 cracked the door open just slightly. In 2007, NASA researchers using high-precision planetary radar found something nobody expected. Mercury has a molten core, not a fully solid core, like you might assume for a small rocky planet that's been cooling for over 4 billion years. Molten, still liquid, still moving. Here's why that shouldn't be possible. Mercury is small, barely bigger than our moon. Smaller planets lose heat faster, the same way a small cup of coffee cools faster than a full pot. By all the normal rules, Mercury's core should have solidified solid long ago. So researchers went looking for an explanation, and they landed on one element: sulfur. Sulfur can lower the temperature at which molten rock and metal solidify, kind of like how salt lowers the freezing point of water on an icy road. The theory was that sulfur mixed into Mercury's core was keeping it liquid far longer than it should be. But that was just a theory based on radar data from millions of miles away. Nobody had actually tested it. Nobody could until now. This year, researchers at Rice University decided to stop guessing and start building Mercury in a lab. Here's the problem they were up against. You can't just study Mercury rock the way scientists study Mars or Earth rock, because Mercury's chemistry is almost nothing like ours. Its surface is iron poor and sulfur rich, and it exists in what's called a chemically reduced state, meaning it's the most chemically reduced planet in the entire solar system. Every assumption built from studying Earth breaks down the moment you apply it to Mercury. So the team, led by researcher Ishan Jong, needed a real-world stand-in for Mercury rock. And they found one in the strangest possible place, a meteorite named Indarch, which crash-landed in Azerbaijan back in 1891. Its chemistry happened to closely match what we know about Mercury's surface. Using that meteorite as a recipe, the researchers cooked up their own synthetic mercury rock in the lab, recreating chemically what might be happening inside the planet itself. And here's where it gets genuinely strange. On Earth, sulfur mostly binds to iron. That's simple, stable chemistry. But Mercury barely has any iron in its crust. So the sulfur had nowhere obvious to go, until the researchers found it was binding instead of elements like magnesium and calcium, essentially taking over a structural role that, on Earth, belongs to oxygen. Let that sink in for a second. Oxygen is one of the most fundamental building blocks of rock chemistry on our planet. And on Mercury, sulfur is quietly doing its job instead. So why does this make Mercury's interior act impossible by normal standards? Because this sulfur substitution doesn't just change Mercury's chemistry, it changes its physics. The researchers found that sulfur lowers the temperature at which these molten rocks begin to crystallize into solid form. In plain terms, magmas on Mercury can stay liquid at temperatures where equivalent rock on Earth would have already frozen solid. Picture two identical pots of soup. One is on Earth, one is on Mercury. Take them both off the heat at the exact same temperature. The Earth pot starts to thicken and solidify. The Mercury pot, because of the sulfur chemistry, just keeps flowing. That's not a small detail. That's the difference between a planet whose interior should have gone solid billions of years ago, and one that's still behaving like it's fighting against solidifying, using a chemical trick almost unique to itself in our solar system. And this builds directly on that 2007 molten core discovery. That radar study suspected sulfur was the reason Mercury's core stayed liquid. This new lab work is the first time anyone has actually shown physically how sulfur pulls that off. Not by guessing from a distance, but by rebuilding Mercury's own chemistry in a lab and watching it happen. Here's the part that goes beyond just Mercury. Scientists have spent decades using Earth as a baseline for understanding every rocky planet. Mars, Venus, exoplanets light years away. The default assumption has almost always been start with Earth's chemistry and adjust from there. Mercury just proved that approach can completely fail. A planet can form right next door to Earth, out of similar raw material in the same solar system, and still evolve using an entirely different chemical rulebook. And that matters for something much bigger than Mercury. Astronomers are now finding thousands of rocky exoplanets around other stars, many of them almost certainly with chemistries we've never directly observed. If a planet one step away from Earth can be this alien on the inside, imagine what's happening inside worlds orbiting completely different stars, under completely different conditions. Mercury isn't just a weird outlier anymore. It might be a preview of how differently planets can form, right under our noses, without us noticing for 50 years. Here's where I have to be honest with you. This discovery raises more questions than it answers. We now know sulfur is doing oxygen's job inside Mercury's magma. But researchers still don't know exactly how deep this chemistry goes, or how it shaped Mercury's crust and mantle over billions of years of cooling. The lab experiments recreate conditions. They can't yet tell us the full history of what actually happened inside the real planet. And there's an even bigger open question. The European and Japanese space agencies currently have a spacecraft called BepiColombo on its way to Mercury right now. expected to finally settle into orbit in 2027. When it gets there, it'll be checking exactly the kind of data that could confirm or complicate everything this lab study just found. So the honest answer is, we just cracked open a 50-year-old mystery, and it led straight to a brand new one. That's usually how the best discoveries in space science work. Not with a clean answer, but with a better question. So the next time someone tells you Mercury is just a boring, scorched rock too close to the sun to matter, you'll know better. It's a planet quietly running on a completely different chemical playbook than every other rocky world we've studied closely, including our own. And in 2027, we might finally get the confirmation we need. If you want to see what happens when that spacecraft actually arrives, or if you want to understand the next planetary mystery scientists are racing to solve, subscribe, because that's exactly what this channel is going to keep digging into. I'll see you in the next one.